Okay, so we are going to continue our review. We've kind of hashed through the basic notation and the notion of the exterior derivative in a very mechanical way, because again, this is a review, so we have to just get the notation under our belts, and hopefully all of this stuff, the meaning and interpretation, is sort of percolating back up into your mind. We've obviously done the basic review of how this all pertains to a manifold with tensor fields of various kinds, in particular form fields, one-form fields, vector fields, tangent spaces, all that stuff. And now we need to review this critical notion of Hodge duality. So with that, let's begin. So I drew up this chart to somewhat show the different basis vectors that we can create using the wedge product and the underlying vector space V. Here I've chosen V to have 4 dimensions. So the basis vectors of V are these 4 differential operators, and the basis dimension of the dual space of V are these 4 one-forms, right? So V itself is constructed from these 4 basis vectors, and the dual space of V is constructed from these 4 basis vectors. And we give this a name. We call this the first exterior power of the dual space, and we call this, let's see, I'll put it over here, we call this the first exterior power of the vector space. And those are actually equal to the vector space itself. This is equal to the vector space itself, and this is equal to the dual space itself. So all linear combinations of these one forms create the one form space, which is the first exterior power of the dual space. Then we can do the same thing with the second exterior power. So this is the basis set of all 2 forms, right? And all 2 forms can be constructed from these 6 basis vectors, and that is given the name the second exterior power of the dual space. This notation comes from Wikipedia. I'm using the Wikipedia notation here. I've seen other notations that kind of play with the superscript or subscript of the degree of the form, but we're going to use the Wikipedia notation. And likewise, you can create wedge products of the basis vectors of the vector space, and you can create the second exterior power of the vector space. And obviously this can go to the third exterior power of the dual space and the third exterior power of the vector space and the fourth exterior power of the vector space and the fourth exterior power of the dual space. And importantly, the basis vector, just the number 1, and all the functions on the manifold, that constitutes the 0th exterior power of the vector space and the 0th exterior power of the dual space. Now, what's interesting to note is obviously these two are actually, these 2 spaces contain the same things, functions on the manifold. So the 0th exterior power of the vector space is somewhat degenerate with the 0th exterior power of the dual space. The first exterior power is just a way of restating the existence of the vector space itself, because this obviously equals the vector space V, and this equals the dual space V. They're the same. Now, but the second, third, and fourth exterior power, those are different. This is a different basis vector. These are all, they have different basis vectors, so they're different vector spaces. Now, there's a couple different ways to move between the different vector spaces in this diagram. And that is, understanding how that movement occurs is actually a pretty important step in understanding how all of this works. But, for example, we can move from the left to the right by raising and lowering indices, right? If we have a metric or an inner product and a metric that connects V and V dual star, you can move in this direction pretty smoothly. There's a one-to-one correspondence between vectors and one forms, between two vectors and two forms, between three vectors and three forms, and between four vectors and four forms, right? And this goes back to what raising and lowering indices is all about. The ability to raise and lower indices allows you to move in this direction. We're not actually going to talk about that here, but suffice it to say let's quickly just review just to make sure you can make contact with what we've studied before. Let me quickly mention how it works. So if we have a two form written out in using the Einstein summation convention, right, where this is the basis vector and this is the coefficient. Now we're using Einstein sum, so we're actually dealing with double counting a little bit, but this has to be anti-symmetric for this to actually to make much sense. So the idea is this guy here lives in this vector space here, right? This guy lives in this vector space. So given that we want to move to this vector space, well, we need to actually raise the indices on it, and we use G alpha nu and G beta mu, and we can now create, by multiplying this coefficient through by these two metrics, we raise the indices to B alpha beta, and likewise this basis vector is going to have to change to partial mu wedge partial nu, like that. So that is how you move between vector spaces from the left and the right. From vector spaces, these exterior powers constructed from the vector space to exterior powers constructed on the dual space. But you must have this metric, and that implies that this vector space here, the V, must have an inner product. We've discussed this extensively in the What is a Tensor series, and I'm just reminding you that this movement here is actually quite trivial. What we're interested in is understanding how to move in this direction, right? So that's what we're going to talk about now. That's what Hodge duality is all about. Okay, so the notion of Hodge duality exploits the fact that the dimensionality of the kth exterior power, in this case the one I'm pointing to here is the first exterior power, is the same as the n-1th exterior power. So there's 4 dimensions in the first exterior power, and there's also 4 dimensions in the third exterior power. So because these two vector spaces have the same dimensionality, it's a reasonable question to say, can I create a correspondence between these two? And likewise, can I create a correspondence between the 0th exterior power and the 4th exterior power? And as far as the second exterior power goes, can I create a correspondence between vectors of that exterior power and itself, right? Now, if I had 5 dimensions here, and I ended up with a 5th exterior power, V star, right, then there wouldn't be a sort of central exterior power, right? There's 2 below it and 2 above it. There would be an even number of exterior powers, and you wouldn't have a central one, and so you wouldn't have this lone central one. But when you do have this lone central one, you want to ask the question, can you create a mapping between it and itself? So that's the question that we're going to answer as with Hodge duality. And for Hodge duality to make a lot of sense, you have to establish what these vector spaces are, meaning you have to decide what your basis vector is of the highest exterior power vector space. In this case, it's 0, 1, 2, and 3. We've established this by choosing that we want all of our vectors to have increasing indices. And when we've done that, now we can create these connections between the first exterior power and the third in particular. That's the one that's of most interest, but also this one, the one between the second exterior power and itself. So now I'm going to provide you the formula that allows you to make this connection. And that formula will take a vector in the first exterior power and find its Hodge dual which is a vector that lies in the third exterior power. And likewise, it'll take a vector in the second exterior power and find its Hodge tool, which will also lie in the second exterior power. Okay, so let's examine that. So this is the formula that we need, and it's this quite grand-looking line of text. And I want to break it down into, it's very simple, actually. But I do need to break down what these things mean, what these epsilons mean, what this sign term means, and how to figure out what to put on the left and the right-hand side. So let's sort of attack it piece by piece using this fancy index notation that we are going to apply here. First of all, I'm just going to teach the formula, right? So this is a review. So the nature of the Hodge dual and how it actually sits, that's for a more complex lecture. This is the formula to help you understand that we can quickly derive the Hodge dual using a very rote method. But the actual nature of the Hodge dual is quite profound, and in a different rabbit hole, we'll go down a whole different way to approach the Hodge dual later on in geometric algebra. But right now, this is just a formula and how to apply it. So let's look at the left-hand side first. The first thing to see is that this star operator is called the Hodge star operator. And the Hodge stars operator, its job is to take whatever is to its right, which is always going to be a form of some kind, and turn it into its Hodge dual. So the left-hand side is the form that's being converted, and the right-hand side is what it's being converted into. All right, so right now, let's look at the way I've expressed the form that's being converted. First of all, you'll notice that it's not a general form. It is just a basis vector. And we're following the idea that, yeah, as a practical matter, if you can find the Hodge dual of the basis vectors, you can find the Hodge dual of anything. You just express whatever it is in the appropriate basis and convert each basis vector to its Hodge dual, and you've converted the whole form into its Hodge dual. That's very classic vector space stuff. If you know how to handle a certain manipulation on the basis vectors, then you can do it for anything. So now how do we express this basis vector? Well, in this case, there's obviously P, right, of these different basis vectors of the original vector space wedged together. So this is a P form. And the index, right, each P form for example, four-dimensional space is either dx0, dx1, dx2, or dx3. Now, for n-dimensional space, this could go on to dx, I guess, n minus 1, right? If you start with 0, right? If you start with 0, you always end up with this pesky n minus 1. But we're looking, this is the total number of vectors in the vector space, or basis vectors in the vector space V. Obviously, if you're dealing with the pth exterior power, right, you end up with this P form. So I guess the way to say it, that this is a P form basis vector. And these indices could be anything, but there has to be P of them, and you can't repeat, obviously, because if you repeated, it would be 0. So you pick any P of these, and you put it in here, and you're asking the question, what is the Hodge dual of that? So you pick the particular P you want, right? You may be interested in dx0 wedge dx1 dx2, in which case you're looking for the Hodge dual of a particular 3-form basis vector, the 0, 1, 2 basis vector. So that explains the left-hand side. So now on the left-hand side, notice you've used up P different basis vectors, which means you have n minus P left that are not showing up on the left-hand side. All of those n minus P's, remaining ones, must show up on the right-hand side, and in this piece on the right-hand side. So whatever is not used here must be used over here. But it doesn't matter what order it's in, right? That's very important. We have a standard preferred order where we want the indices to be increasing. So in our preferred order, it would always be the case that I sub 1 is less than I sub 2, which is less than ... to I sub p. And likewise, we would expect this index to be less than this one, etc., all the way to be less than in. But it doesn't have to be, right? It turns out this formula will work regardless, right? In fact, all of this machinery over here is just to get the sign of everything correct, which has to do with essentially reordering everything one way or another. So whatever is missing from here must be here. And that shows you the correspondence we're talking about, right? If this is a P form, then it must be that this over here is an n minus P form, which is exactly what I advertised would happen, right? This is a 1 form. You end up with a 4 minus 1 or a 3 form, right? If it's a 2 form, you end up with another 2 form. 2 and 4 minus 2 is 2. If it's a 0 form, you better end up with a 4 form. Or likewise, it can go the other way, right? If you started with a 3 form, what's left over is going to be a 1 form. If you started with a 2 form, you're going to get another 2 form. If you started with a 4 form, you're going to get a 0 form. So that's enforced by this equation. Whatever is not used over here must be used over here. And then all that remains is to understand this. And this comes in 2 parts, sort of the easy part and the more subtle part. The easy part is you just line up all the indices in the actual order that you laid them out in the formula. I1 through IP, all the way goes in the first P slots, and then IP plus 1 to IN goes in the remaining slots. So this expression here is actually sine I1, I2, ... to IP plus 1, ... to IN, right? So this sequence here is exactly this sequence followed by this sequence. So whatever sequence you chose for the basis vector you wish to seek the Hodge dual, you line those up as the first P, and then the remaining ones that you've chosen that go P plus 1 to N, you line up as the remaining P plus 1 to N, or N minus P indices. So then you have a string of numbers here, right? And these numbers might be, let's see, I'll just give an example, right? This might end up being, let me erase this. This might end up being, for example, the sine of, say, 2, 0, 1, 3, 3, like that. In which case you are looking for the Hodge dual of dx2 wedge dx0 wedge dx1. And on this side, you end up with what's left over. Well, the only thing that's left over in a 4-dimensional vector space is dx3, right? So you end up with this question of what is the sign of this sequence 2, 0, 1, 3? And the answer is it's either plus 1 or minus 1, right? It's plus or minus 1, and it depends on whether this is an even or odd sequence and relative to the standard sequence 0, 1, 2, 3. So it's just how many flips does it take to get this thing into this order. And if it's an even number of flips, you get a plus 1. If it's an odd number of flips, you get a minus 1. So in this case, I have to move the 2 over once and over twice. So this would be an example of a plus 1 sign. So this sign term comes as a plus or minus 1 to compensate for how this overall sequence compares to 0 through n in order. And what that's basically saying is when you go back here, you've chosen this highest order K form, the 4 form. You've chosen that as your definitive basis vector. So this becomes sort of the reference sequence of numbers, 0, 1, 2, and 3. Once you've chosen this, everything needs to conform to that. And in order to conform to this, because this is an arbitrary choice, I could have chosen dx1, dx0, dx2, dx3. if I wanted to. But we like to do this increasing order sequence thing. So when we do that, we end up introducing this sign term to kind of keep track of how you may be organizing your basis vectors on the left and right of this equation. So that takes care of this term. It'll give you a plus or a minus 1. Now these epsilons are a little bit more subtle. The epsilons are concerned with what is the value of the inner product of a basis vector with itself. So if I go back, I will show you how this is defined here. Epsilon of mu is the inner product of dx mu with itself. And so it would be epsilon of 0 would equal dx0 dx0, which in our convention is equal to minus 1. But epsilon of 1, epsilon of 2, and epsilon of 3, all those are going to just equal the number 1 in our convention. In Minkowski space, the metric drives this guy to be minus 1 in our convention, and these three guys to be plus 1. And so that's the meaning of epsilon mu. And so you see that the formula that we're working with includes the epsilon mu values of all of the basis vectors that are on the left-hand side. The left-hand side, I1 through IP. So you have epsilon of I1 all the way to epsilon of IP. And these will only give you a minus 1 if, at most this can give you either no minus 1s or 1. And because remember, you can't repeat an index, so E sub 0 is going to appear only once here if you're dealing with Minkowski spacetime. The beauty of this formula is that's completely general. It's leaving open what your metric is. You might have a metric with, I don't know, you might be playing with some, strange space-time or a strange concept where, there's two time directions. So there's two different basis vectors with a negative sign and two with a positive sign or something crazy. But in Minkowski space, you're not going to deal with that. So that is how the formula is structured. And now we will apply it with some examples. I've written out a whole bunch of examples right here. So let's begin with that. All right, so on this big old chart, I kind of did a bunch of examples. I've chosen the examples from Minkowski space in R4. So we have a four-dimensional vector space, V. And noting that in Minkowski space, the zeroth basis vector is going to come in with a minus 1, meaning its inner product with itself is minus 1. But all the others, the epsilon for values for dx1, dx2, and dx3, those are all going to come in with a plus 1. But I also wrote it down for Euclidean space. And in Euclidean space, they're all going to have a plus 1. Right? So there's going to be no minus 1 there. And Euclidean space also, I'm just considering 3 dimensions, not 4 dimensions. So let's look at some examples of exploiting this formula. Here's the actual formula that we learned. And let's just begin with looking for the Hodge dual in Minkowski space of just the one form dx0. Now, it's 4 dimensions, and dx0 is on the left-hand side. So we know on the right-hand side, we've got to have the 3 missing vectors. So it's going to be dx1, dx2, dx3. And I've just chosen it to be in the easy order 1, 2, 3. But I could have chosen them to be in any order, right? Because this sign would have changed if I'd picked some other order, maybe. So the sign expression is simply x0 followed by, it's the left-hand sequence followed by the right-hand sequence. Well, the left-hand sequence is just 1, and the right-hand sequence is 1, 2, 3. So I'm doing sine of 0, 1, 2, 3. And that is exactly 0 permutations away from the standard sequence of 0, 1, 2, 3. So this just gives me a plus 1. And then I take the epsilon value of all the basis vectors that are on the left-hand side. Well, in this case, it is this exceptional one where you pull a minus 1. So epsilon 0 is equal to minus 1. So all of this stuff here gives me a minus sign, and the Hodge dual of the basis vector dx superscript 0 is this 3 form, the dx1, dx2, wedge dx3 with a minus sign. So that tells me right away that if I go to dx0, I can map it to minus dx1, dx2, dx3. I actually did this mapping earlier, so I'm guiding it right here. So that is one of the 4 done, right? And I can do an example for dx1 similarly. Now I wanted the Hodge dual of dx1, so I have to create it out of the 3 remaining ones. I'll choose it to be in increasing order, so it's dx0, dx2, dx3. So I know that the Hodge dual of a 1 form should be an n-1 form. Well, n is 4 for our Minkowski space, and minus 1 is 3. So this is a 3 form, and sure enough, there it is. And it contains all the ones that are not dx1 wedged together. Now I have the sign of this sequence followed by this sequence. So I have 1, 0, 2, and 3, which is 1 sign flip away from the standard form of 0, 1, 2, 3. So that picks up a minus sign. And I do not get a minus sign from epsilon 1 because epsilon 1 is 1. So now I have the Hodge dual of dx1 is minus dx0 wedge dx2 wedge dx3. And likewise for dx2, same thing, right? dx2, I pick 0, 1, and 3, which does not include 2. I now have the sign of 2, 0, 1, 3. That requires 2 sign flips, if I've got this right. 1 to get the 2 over here, and then another. So there's no sign is picked up. No sign is picked up from this. No sign is picked up from epsilon of 2. And so now I have the Hodge dual of dx2 is dx0, dx1, dx3. And likewise, for dx3, I end up with a minus dx0, dx1, dx2. And that's sort of the art of this thing, right? The right-hand side contains the wedge product of everything that's not on the left-hand side with some sign that's calculated by this formula. Now, if I was in Euclidean 3-dimensional space, it's a lot easier, right? Well, it's not a lot easier. It's not a lot easier or harder. The point is these epsilons don't even matter because they're always 1, right? There is no such thing as a -1 because the metric is so simple. The metric is always positive. So I can almost ignore those epsilons now. But now I'm only dealing with 3 dimensions. So the only thing that's missing, I guess I called the 3 1, 2, and 3, not 0, 1, and 2. And that's fine because when you have a 0 there, you usually are implying Minkowski spacetime and epsilon of 0 should be -1. So now with the Hodge dual of dx1, the remaining ones is 2 and 3. Sign 1, 2, 3 is going to give you no additional sign, so it's just dx2, dx3. With dx2, your sign is going to be dx as 2, 1, 3 if you choose dx1 and wedge dx3. And epsilon 2 doesn't count, so you do pick up a minus sign. Now, if I had chosen dx3, dx1 here, right, then I would have had I would have had no minus sign here because I would have had dx2, 3, 1, and that would have been 2 sign flips to get it back to normal, so that sign would have gone away, but this would have ended up as dx3, dx1. But, I could write that as dx3 wedge dx1 anyway, because I know whenever I flip the order of a wedge product, I flip the sign. So that's not a big surprise, right? And then likewise, I can find the Hodge dual in Euclidean space of this 2 form, dx1 wedge dx2. What's missing? Well, dx3, but dx3 is a 1 form over here. And these 2 don't matter because they're always 1 in Euclidean space, and I have a 1, 2, 3 sequence, so there's no sign flip there, so I have dx3. Likewise, I can find the Hodge dual of everything else here. And of note, the Hodge dual of a function a function is the Hodge dual of a 0 form, and that is going to be a 3 form. We just apply the same formula. There's none of the vectors appear on the left, so they all must appear on the right. And I choose the order 1, 2, 3, so the sign doesn't add anything in there, and these epsilons don't matter either. And so I just have F as a coefficient to the basis of the 3 form. Now, in Minkowski space, you have the only complication that you end up with these E0s every now and then. But if I wanted the Hodge dual of the 3 form 0, 1, 2, what's missing? Well, dx3 is missing. So now my sign is 0, 1, 2, and then followed by 3. It's this sequence followed by this sequence. Well, that's not going to give me a sign change, but I do epsilon of 0, epsilon of 1, epsilon of 2. 1 and 2 don't matter, but epsilon 0 gives me this minus sign. And so I can calculate all of the Hodge duals of 3 forms, and they're all going to be these various 1 forms. Now, what I didn't show here is the Hodge dual of a 2 form. So let me do that real quick. So just to make it interesting, I'm going to take the Hodge dual of dx2 wedge dx0. Now, this is not a standard basis, right? Because we have a decreasing set of indices here. But just to prove to you that it doesn't matter, let's work it out. So what's going to be on the right-hand side? Well, the first thing is what's remaining on the right-hand side. Well, we're missing 1 and 3. So let's just do dx3 wedge dx1. Again, I'm not choosing the correct sort of canonical form. I don't know if canonical form is the right way to say it. I'm not choosing the increasing convention here, which just to show that it works fine. So I will take this sequence followed by this sequence. This is what fixes everything. So it's going to be 2, 0, 3, 1. And then I'm going to take the epsilon value of 2 and the epsilon value of 0. So 2, 0, 3, 1, I just look at 2, 0, 3, 1. Well, I want the order 1, 0, 1, 2, 3. So I do one flip to get the 0 there, so that's a minus 1. And then I have to do another flip and another flip. So this first flip will make it a plus 1, and this flip will make it a minus 1 again. So this guy is going to introduce me a minus 1. But then I have a minus 1 from here, so that all goes away. So I know that this equals dx3 wedge dx1, which, if I want to put it in my nice order, I make now minus dx1 wedge dx3, like that. And so that just shows you that now the Hodge dual of a 2 form is an n minus 2 form, but n is 4. 4 minus 2 is 2, so it gives me another 2 form. And notice how these signs all are taken care of in these coefficients here. So I don't have to worry about this increasing order element of things, although it is probably good practice to stick with it. Okay, so that is how we find the Hodge dual of all this stuff, how we move between n forms and n minus p forms, which can go in these directions. You can't just move steadily in this direction using Hodge dual. Hodge dual jumps you from 1 forms to 3 forms, 2 forms, it keeps you inside 2 forms, and it goes from 4 forms to 0 forms. But this is very important because now we are going to take electromagnetic field elements and we're going to associate them with vectors. We're going to pop over, then associate them with dual vectors, and then we're going to freely move between these dual vectors and their Hodge duals. So this is dual vectors, and this is Hodge dual, right? So there's 2 different uses of the word dual here. Dual is always this notion usually of moving between different vector spaces. So, and then we're going to broker all that to decide how to call magnetic fields and how to call what to call magnetic fields and what to call electric fields, and we're going to create some expressions for Maxwell's equations using the language of forms and the language of Hodge duality. Well, Hodge duality is part of the language of forms, I guess. So that is our next project, right? Our next project is to take what we understand about forms. Now that we understand Hodge duality, we're going to start doing this and take Maxwell's equations and turn it into expressions involving nothing more than forms and dual forms, Hodge dual forms, all right? And so that will help us create a slightly simpler form of Maxwell's equations, one step simpler than the tensor form that we learned in the 2 lessons ago. All right, so I'll see you next time.